Okay, so we're well into our development of the finite-dimensional weak form for our linear elliptic problems in 3 dimensions with scalar variables. We are in fact at the point of having already decided to work with hexahedral elements, and I've stated that these will be constructed from by a mapping from a parent domain. Okay, so let's just pick up right there. So mapping from the parent domain, which I've already said we are going to continue to call omega xi, to omega e. Okay, so here's what we have. We have omega e, and I'm somewhat purposely going to draw this as an irregular hexahedron. So maybe something like that. Okay, let me see. Okay, that's reasonably irregular as a hexahedron. Okay, 8-noded still. Okay, but now the point is that we say that this is obtained from a mapping from a domain in which things are indeed regular. So we have a nice cubic domain, a nice cubic structure in the parent domain here. Okay, so this is where we are constructing this element omega e from, right? And this is omega sub c. Now, in this domain, since this is 3-dimensional, we have coordinates xi, eta, and zeta. Okay, and in terms of xi, eta, zeta, again, this is a bi-unit domain. Okay, so omega xi is also a bi-unit domain, just as we had in 1D. Okay, what that means is that in terms of coordinates of the nodal points in this domain, we have, for these nodal points, we have the following coordinates. Okay, so this point here is -1, -1, -1. This point is 1, -1, -1. This point is 1, 1, -1. And this point here is -1, 1, -1. Okay, on the top surface we have 1, -1, -1. I'm sorry. This is -1, -1, and 1. This point here is 1, -1, 1. This is 1, 1, 1. And this point here is -1, 1, 1. All right, so these are the points, and you note that in general, each of these points can be referred to as C, A, eta, A, and zeta A, right? Where A, once again, runs from 1 through 8. Okay, but here it matters that we establish a numbering. Okay, so let's what I'm going to do is, just so that we can distinguish things, I'm going to use a different color here to mark our nodes. Okay, so I'm going to write the local node numbers. There are only local node numbers, of course, in the parent domain, but we're going to call them 1, 2, 3, 4, 5, 6, 7, 8. Okay, those are the values taken on by A in the parent domain. Okay, once we have this, what we need to do next is go ahead and construct our basis functions. Okay, the basis functions that we have are going to be written again in terms of C, eta, and zeta, and I'm just going to list them right now. Okay? So with things set up in this manner, in general, we have this formula, NA as a function of C, eta, zeta, right, is equal to, sorry, I need more room here. Okay, NA is equal to something expressed as a function of C, eta, zeta. Okay, and here we're already taking this approach that though we originally introduced our basis functions NAs as being parameterized by physical coordinates, we are thinking of them as physical positions in turn being parameterized by positions in this parent domain. Okay, so here is the general formula for them. NA is 1 over 8, okay, 1 plus C times CA times 1 plus eta times eta A times 1 plus zeta times zeta A. Okay. If you look at this form, what you will notice is, if you also recall the way we wrote out our Lagrange basis functions, Lagrange polynomial basis functions in 1D, right? In 1D, we had only one of these contributions. Okay, here in 3D, we have three of them. It's just multiplied together, and this particular way of constructing our basis functions is called a tensor product approach. Okay, so the NAs are, so the NA written as a function of C, eta, and zeta are what are called tensor product functions. Right? The idea is that you take your basic form established in one dimension and just extend it by multiplication to the other two dimensions. Right? And the factor of 1/8 will, of course, account for the fact that we have 1/2 to the power 3, okay, for the 3 dimensions. Okay, perhaps for clarity, it's actually useful to write out the basis functions explicitly. And that's what I'll do now. Okay, so here we go. N1, function of c eta zeta is 1/8 times 1 minus c times 1 plus eta times 1 plus zeta. N2, function of c eta zeta is 1/8 times 1 plus c times 1, sorry, these are both minus 1 minus eta, 1 minus eta there. Okay, so it's 1 plus c, 1 minus eta, 1 minus zeta, and 3 equals 1/8 1 plus c times 1 plus eta times 1 minus zeta, and N4 equals 1/8 1 minus c 1 plus eta 1 minus zeta, and 5 1/8 1 minus c 1 minus eta 1 plus zeta, and 6 equals 1/8 1 plus c 1 minus eta 1 plus zeta, and 7 is 1/8 1 plus c 1 plus eta 1 plus zeta, and finally N8 is 1/8 1 minus c 1 plus eta 1 plus zeta. Okay, that's the whole lot of them, all right, all written as functions of c, eta, and zeta. Now, if you look at these, you will immediately see 2 properties that follow, right? From these, we directly get the Kronecker delta property, okay? So, NA evaluated at C, B, eta B, zeta B, okay, is equal to delta AB, the Kronecker delta. All right, and we also have this other property, which is that the sum over all shape functions, right, at a point right, at any point indeed, is 1. All right, properties that were identical to what we saw in 1D. Okay, the second property allows us to represent constants. The first property is the one that gives us this interpolation property also of these Lagrange polynomial basis functions. Okay, so I should probably state here these are Lagrange polynomial basis functions in R3 in 3 dimensions. Okay. All right. And also you note why they are trilinear. Okay. Note the trilinearity. Right. It's each of these functions is linear in each coordinate, right, for the 3 coordinate directions here. Okay. So these are the functions that we use to construct our finite dimensional trial solution as well as finite dimensional weighting function. Okay. And furthermore, looking ahead, we also are going to use the same basis functions to interpolate the geometry. Okay, so the actual map, okay, the map from omega c to omega e, okay, is obtained by really interpolating x as a function of c, and here I will use the general notation c as a vector to represent the nodal coordinates c, eta, zeta. Okay, so the map is obtained by interpolating c, x as a function of c, right, where I will say that c, I'll state it the very first time and we'll use it in the future, right. We get this interpolation by simply observing that x, a, e parameterized by c is now simply, x, e parameterized by c, which is any point in the physical element subdomain, right, is obtained as an interpolation a equals 1 to number of nodes in the element, Na depending upon the coordinates in the parent subdomain, okay, multiplied with the actual nodal coordinates, right, in the physical subdomain, but where I've used the local numbering of nodes. Okay. All right, so these are, we just remember that these are just nodal coordinates in physical domain. Right, and that means we are talking of for that element omega e, we are talking of a typical nodal coordinate as being that one. Right? We interpolate over all of those and we get any point inside here, x, e. Okay? That's how things work, and that is constructed from a mapping from our nice regular, at least this is intended to be regular, parent subdomain. Okay, so that is the mapping that we have underlying our geometry as well. And you remember the term for this kind of a formulation. This is, remember, right, it's called an isoparametric formulation. Okay, isoparametric referring to the fact that to interpolate our finite dimensional weighting function as well as the geometry, we're using the same basis functions. Okay, so we have an isoparametric formulation. With this, we know how to go ahead now. We will be able to compute our fields, including their gradients, right? And we'll end this segment here, but when we come back, we will look at how to use this isoparametric formulation to go ahead and compute gradients and so on, and also do the integration. The approach is going to be exactly what we did, exactly like the one we followed in one dimension, except that we basically need to generalize all those ideas into 3 dimensions. All right, we'll stop here.